Don't put these pants like that.
Did you get my findings? Yeah. Oh, yeah. Yeah.
Guys, I think I might go ahead and try to get started here. Good afternoon. It's great to see everybody again today. I always worry after the exam if anybody will come back. I guess you're all enrolled now, so you're stuck with me.
Before that nice.
Exactly. Anyway, I did get your exams done. I will tell you, I did not go home last night until about 2 a.m. So if I look a little tired today, yeah, I sent a very late email. I was bound and determined that I was not going to carry it over till today, and I wanted to get some done. But I will give you back your exam, but not till the end of class. I'm sure you know that if I pass it back right now, nobody will pay any attention to me for the first 15 minutes while they flip through their exam. So I'm going to wait until the end of class to pass them back. I did post the solutions to the exam in Canvas, and I also emailed them to you. At least I wrote out a solution guide that I think is pretty accurate, hopefully. Yeah, so I'll talk about the exam at the end of class. Overall, it's very good. I was quite happy with the results, but there's of course always a few little blind spots that deserve a little mention. So I'll try and save 5 minutes at the end to do that. I won't go over the exam though in class. I'll just ask you to read the solutions on your own. Hopefully you learned a little bit from it and also feel a little bit better about kind of all the stuff we did in these first, whatever, 6 weeks of the semester. So anyway, appreciate all your hard work on that. We'll go another 6 weeks or so, I think, and then have another midterm right before Thanksgiving is the next exam. So what we're going to do today, you notice there's no recap on the board. That's usually only going to happen when we're starting a totally new topic and there's nothing to sort of carry over from the previous class. We are going to start a new topic, which is going to be in chapter 7. So we're jumping to chapter 7. Of course, we're skipping certain topics from the earlier chapters. We just don't have time, obviously, to cover absolutely everything. So yes, and this is going to be on the subject of recurrence relations. So this is another very combinatorial topic. You're going to see it in pretty much any combinatorics class. They're probably going to try to talk to you about this topic a little bit. You know, most of these problems that we've learned how to solve so far this semester, these counting problems, are really a function of some size of the problem. Like maybe it's a photograph of 6 dogs and cats, or maybe it's 7 dogs and cats, or maybe it's 8 dogs and cats, right? There's some underlying integer that kind of controls the problem. And then you might imagine trying to generalize and ask, well, how many photographs are there with n dogs and cats? As you might wonder, could I come up with like a general formula, right? N could be any positive integer, 2 cats, 3 cats, 4 cats, 5 cats, whatever. So, and often the answer to one of those problems could be solved in terms of another one. So if I knew how many ways there were to take a picture of 7 cats and dogs, I might be able to build from there and figure out how many ways there would be to take a picture of 8 cats and dogs. Because I'm only taking the problem I already know how to solve and adding one more object into my photograph. And so that is the idea behind recurrence relations, is that we're going to relate sort of as some function of n, which is a variable positive integer, we're going to relate one version of the problem for n objects to, say, the same problem for a smaller number of objects. So a recurrence relation actually is nothing more than a relationship between a sequence of numbers, right? And so let's start writing some notes on that, but that's kind of the motivation behind it. So I'll just start off maybe with a definition, and then of course we'll do a bunch of examples as well. But a recurrence relation for a sequence, I'm going to say H0, H1, H2, H3, and dot, 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 a sequence of numbers. So if we have a sequence of numbers, maybe HN is the number of photographs involving N cats and dogs, right? So that would be some number, but we might want to know, well, what if there was one cat or dog? What if there was two? What if there was three? What if there was four? This is a whole sequence of answers to a bunch of problems that are basically the same problem. It's just the number of objects could change. So a recurrence relation expresses H sub n, right, which is the nth term, in terms of previous terms. The previous terms, of course, being Hn minus 1, Hn minus 2, and dot, dot, dot. We could go all the way down to H1 and H0. Sometimes the recurrence relation might not start at 0. So here I'm pretending like you could start with 0, but obviously if I say I want to make a photograph of 0 cats and dogs, that isn't really a physically meaningful problem, so it might not make, you might just prefer to start with H1 in that case where you actually have an object. But in theory, you could start your sequence with 0. So maybe I could give you an example of this. The idea behind this is that if you can relate Hn to smaller versions of the same problem and solve those problems, then you can build up to combinatorics problems that are harder and harder to solve directly. Another way of saying it is you can take your problem and break it down into easier and easier problems to solve with smaller numbers of objects. So generally, this isn't going to be helpful if you can't at least figure out what H0 is directly, or what H1 is directly, or something like that. So as an example, a recurrence relation for Hn equals, let's say n factorial. So that will be my sequence. So my sequence is just 1, 1, 2, 6, 24, 120, 720, just all the different factorials, is given by. Does anybody want to tell me? I think a lot of you already know because some of you did it on my exam the other day. How could you write n factorial in terms of a lower factorial? Finish?
Times n minus 1 factorial.
Exactly, n times n minus 1 factorial, and I'll rephrase that as h sub n minus 1. Okay, so let's say I don't know how to figure out what n factorial is. Well, I could maybe figure out what n minus 1 factorial is and then solve for what n factorial is. And I could kind of do it in that sense. But whenever you have this kind of a recurrence relation, you generally will want to provide what I like to refer to as initial conditions. Like, what is H0? Like, if I was to kind of use this to help me figure out H sub n, eventually I'm going to break it back down in terms of like H1 or H0 or something. So it's always good to have an initial condition. So you might do it like so. H sub 0 is equal to 1. So this just means that the first or the 0th term of your sequence is 1. And then from that, I can figure out what H1 is, and then what H2 is, and H3, and so on. Okay, so a recurrence relation is it's an expression for H sub n in terms of the previous terms, but it's also usually going to be accompanied by an initial condition. Or they might ask you to, you might have to figure out what is the initial condition. Here, 0 factorial being equal to 1 is just sort of a convention. But if it was an actual combinatorics problem, maybe you'd actually have to solve for what that initial value was. We can give some other examples of recurrence relations. This is just a very easy one that's maybe familiar, the factorial function. But even the other day on your exam, I had a formula for the derangements dn, and you may remember what it was. It was actually not that different from the factorial one. D sub n was just n times dn minus 1 plus -1 to the n. Now, of course, I wasn't asking you to solve that for that recurrence relation at the time. I was actually asking you to prove this recurrence relation from the formula, right? And of course, here we would also want to have an initial condition, the number of derangements of, maybe I'll just use n equals 1. There's no way possible to derange just one object, so you could include d1 equals 0 there. So I'll just say here C midterm 1, because we had a little question on that. In no way, shape, or form, though, are these recurrence relations unique. You might wonder, is there only one way to do this? And that is certainly not true. I can give you another one that you're also familiar with, which is that we did this one in the homework. dn equals n factorial minus n choose 1 times dn minus 1 minus n choose 2 times dn minus 2, and then minus dot 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 all the way down to the last term, which is n choose n times, I guess I did use d0 here. So d0 was equal to 1. I think that was the convention. So do you remember this homework problem? It's on the most recent homework. It was not written this way. It was written with n factorial on one side of the equation. You did a combinatorial proof. All permutations can be thought of as permutations that derange everything, plus permutations that derange all but one object, plus permutations that derange all but 2 objects, and so on. So you've done that one. For those of you, so this was on homework number 5. And for those of you who came to my review session, I was trying to help you get ready for this problem in the review session, because I think I did this one in the review session. dn equals n minus 1 times the quantity dn minus 2 plus dn minus 1. So this was another one that we explored for those of you who were at the review session. So I'll just say from the review session for the midterm. So that was another example. So you can have lots of different recurrence relations for the same sequence, And these are just 3 examples involving the derangements idea. Our purpose in discussing this really is going to be that we want to use recurrence relations to solve counting problems. Right? And in order for us to be able to do that successfully, there's going to be 2 things that we have to sort of train ourselves up to be able to do in chapter 7. One is, how do we come up with the recurrence relation in the first place? Of course, here these have been all given to us. But if we didn't have a recurrence relation for the number of derangements, how could we come up with one? So finding a recurrence relation. And the second part of that coin is, well, once you have the recurrence relation, how do you solve it, right? So if I gave you this, let's say you didn't know this was coming from n factorial, and I just gave you this and this. And I said, what's h sub n? What's the explicit formula? That would be the second part of this coin. First part is coming up with this in the first place. The second part of it would be, how do you actually solve it? So let's write that down. Just so we have the game plan in the notes here. I think that would be good for the motivational purposes anyway. So to use recurrence relations effectively to solve counting problems. We must, first of all, so 2 steps. First thing is we need to create the relation. Create the recurrence relation from the physical problem. So whatever the problem is that we're solving. So like, I think probably the easiest one here is the one in the middle, right? I could say, I would like to come up with a recurrence relation for the number of derangements of n objects. I could say, how could I do that? Well, okay, I could imagine the number of derangements of n objects being all permutations minus the ones that are not derangements. And then I can kind of think of those in terms of deranging fewer of those n objects, right? And so then you could maybe, I mean, I think, you know, if maybe not 2 weeks ago, but now if you thought about this equation, you say, yeah, that equation kind of makes sense. It kind of makes sense, right? I'm just looking at choosing which objects are, well, I'm choosing to derange a certain number of objects, and I'm choosing which objects I'm not deranging. I think we could probably make that happen. So we're going to practice this one, creating the recurrence relation from whatever problem we're trying to solve. And then the second point, as I was just saying, is we must also be able to solve the recurrence relation. So it's not going to do us any good to develop recurrence relations unless we can get some tools for how to solve them as well. So to use these things to help us with these combinatorics problems, we're going to have to be able to create them and then solve them. It's kind of the idea. So let me try to give you an example of that. So this is a fairly famous example that I'm going to try. It involves a little bit of a picture though. So I'm going to hope that my drawing is going to be okay here. This example of kind of this program that we're going to be exploring, this 2-step process, is going to be, I'm going to use something called the Towers of Hanoi. This is a famous problem. If you Google this, you'll find all sorts of stuff about it online. So the idea here is it's just a little game where you have, so some of you have heard of this, you have sort of 3 pegs. I'm just going to draw these little pegs here. And then you are arranging objects on these 3 sticks. These are just like 3 sticks. And at the start of the problem, all of the objects are stacked in the middle peg, and you have there is one important rule, which is you can never have a larger object on top of a smaller one. So on this middle peg, you maybe have a very large disk here, and then a slightly smaller disk above it, and then a slightly smaller disk above that, right? They have to be kind of stacked up. So you just imagine these are like, I don't know, Frisbees that are like piled up with different diameters on this middle pole here. Okay, and so the way that this problem works is we can let, I'm going to use this notation, let m sub n be equal to the minimum number of moves required to move n objects to a different pole. So these are 3 poles here. These are the poles. I hope my picture is making some sense. Okay, so again, the rules here, I know some of you already know this, just in case you don't, just to save you a quick internet search, I'll just tell you. The rules are just that a larger object can never be placed on top of a smaller one. So as you're making these moves. As you're making these moves, you have to make sure that you never stack a bigger object on top of a smaller one. So like, I can't move this second object until I move the first object. So like one move might be to move that first object right over here. So we take it off of there and we just move it over to here, right? But then the second object here cannot be placed on top of that one because it's bigger. So the only place you could move this one would be over here, you see, right? So then it's moved over there. And I would like to move this one off of here because I'm trying to move the whole stack to a different pole. But unfortunately, this object is bigger than both of these two. Right? So I have to move this small one over to here first to clear space, an empty space here, where now I can take this object and put it over here on this side, right? I should have just brought a whole stack of toys. That would have been better. You kind of get the idea though. And then after that, I can't move this one off of the center pole until there's a place to put it. And all of the objects on the sides are smaller than this one. So I have to get both of these stacked back up over here again. And in order to do that, obviously, I got to get this one over here. Well, that means I got to move this one out of the way. So you can kind of see that the question, the problem is, the problem we're trying to solve is find a formula for the number of moves, minimum number of moves that you would need to use, and this would be for all n. That's kind of the problem that you're trying to solve here. Okay, so I'm gonna try to practice my little two-step program with you here on this example. So the two-step program is, the first thing I need to do is come up with a recurrence relation for this problem. I would love to explain how m sub n is related to m sub n minus 1. Right? So, you know, if I go back to my original stack of objects here, so kind of start over for a second. If I start over, what I can do, guys, is I can just imagine. Does anybody know the strategy here? Like, what do you, how could you explain what m sub n is in terms of m sub n minus 1? Yeah, Abby?
So you have to recreate the n minus 1 stack
That stack.
in, let's say, the left one, if we're aiming to end up in the right one.
Okay.
So then you n minus 1, and then you move the middle one to the right one, and then you recreate n minus 1 again.
And
On
then
top
you
of that
move
one.
that over there. That's exactly right. So you take all of the objects except the bottom one, and you just do a mini Towers of Hanoi with those. So that's n minus 1 objects. So you move all of those out of the way so that this one on the bottom, right? So what Abby said is that you're going to move that one over here. But before you can move it over there, these other n minus 1 objects have to be out of the way. So you use this many moves. We don't know what that is yet, but you use that many moves to take the top n minus 1 objects and move them over here. Then you move the bottom one across, and then you have to restack this pile of n minus 1 objects on top of the one that you just moved over to here. Okay, so what would be that relation then? So solution here, a recurrence relation for m sub n is, anybody want to take a stab at it? Besides Abby, because I think she probably knows. Like, you have to think, like, how many moves is it gonna take?
Just a question on.
Yeah.
When you get to that n minus, or n minus it's 5. The bottom is.
Uh-huh.
That would be like the block. N minus, or n minus 1 other discs.
Not in one move, no, you have to, you can only move one object, I guess I should have been clear. You can only move one object at one time from one pole to another. You can't take the whole stack of them and move. So once the biggest one has been moved over here, you still have to take all of the other n-1 and get them over there as well. And you can only do it by this process of one peg or one object at a time, one move at a time. Yeah. Okay, you wanna give it a try? That was pretty reasonable to me. So basically, the idea of this formula here, right, 2 times m sub n-1 plus 1. The idea is that you first have to move the top n-1 objects in a sort of mini Towers of Hanoi problem. The plus 1 is where you move the biggest object from the bottom to the open pole. And then you have another m sub n-1 moves to get those n-1 objects moved on top of that biggest object. Does this make sense? Kind of reasonable? He? So these top n-1 objects, I have to move them over here first. That's already one time of doing this many moves, right? So I move them all over there, but I can't just move this last object, the biggest one on the bottom. I can't move that over there because it's not allowed to be on top of all of these smaller objects above it. So I have to move this big one way over here to this side. But then I'm not done yet, you see. I'm not done yet because I have my big object way over here and I have all of the rest of the stack way over here. So they're still split apart and I still have this job. I have to take this stack of these guys and now move them over to that pole. So you're moving the whole stack of n-1 objects twice.
And so one would be just one. We wouldn't even know about
Yeah.
that.
Yeah.
Do we need to have a physical example?
Yeah.
You guys can play with this problem at home. You just need some objects.
There's a website too where you can,
Really?
yeah,
Oh, so if you go to a website, you could probably take a look
you
at
can
this.
probably find it, Google it. on the
Yeah.
side.
So I can
See
put
if I can find it.
that on top, yeah. So anyway, so you could sit at home and play this game with like 5 objects, put them in the middle, right? And then just start saying, okay, I'm gonna move this one here, I'm gonna move this one here, then I've got to move this one over here, then I move this one here, I keep going like this, right? There, there, see how good I am? So you just do it, but eventually, all of these objects, except for the one on the bottom, the biggest one, have been moved to another pole. Now I have to move this over here. That's one move. And now I have to take this whole stack and move it again back over to here. Okay?
It's not like that.
Yeah, so maybe it's better than trying to draw the picture. Yes. Not yet. That's our goal.
Oh.
Our goal is to solve this counting problem, to find a formula. So what I've done so far is I have found a recurrence relation for m sub n. That's step 1. So let me just say a quick word of explanation here. So the idea here is it takes m sub n-1 moves to restack the top n-1 objects on another pole. Then it takes plus 1 move to move the bottom object, just move that one last object that was at the bottom to the available pole. There's only gonna be one more available pole. So we do that, and then finally, it takes another m sub n minus one moves to restack the top n minus one objects on top of the bottom object. But this is in words, maybe what you could say. So that's an explanation for the recurrence relation. You add those together and that gives you the formula there. Now, if I actually want to explicitly solve for how many moves this puzzle takes to solve, there is something else I probably should write down before I go too much further into this solution. And what might that be? The initial condition. Well, of course, n could be anything. Yeah, we don't know. It just depends on what it is. But I would also want to have an initial condition. And when you're doing these initial conditions, guys, please try to make sure that the initial condition corresponds to a case that actually makes physical sense. So when we're talking about the factorial one, of course, I don't care if you want to use 0 as your initial condition, that's fine. But I wouldn't want to like write down m sub 0 here because I don't really know what it means to like play this Towers of Hanoi game when I don't have any objects at all. I mean, I guess you could define it to be 0, but it makes more sense, I think, to imagine you had one object. And if you had one object, how many moves would it take to move it from one pole to another? Just one, right? So this would be good to include as well. Okay, so all of this is sort of the step 1 of my 2-step program over here that I'm describing for how we're going to solve counting problems. So now I'm going to take a look at step 2, assuming everybody is okay with step 1. I will tell you that of these 2 steps, step 1 is usually the harder one, I think, for most people, because you have to be a little bit creative. Like, how do you think about this puzzle in order to come up with that recurrence relation? The second step, when you actually want to solve the recurrence relation, those techniques tend to be a bit more cookbook. There's sort of like a procedure. If the relation looks like this, then you do this. And if it looks like that, then you do that. And there's kind of a pretty standard set of techniques for solving them. What I'm going to do here is, I'm going to do step 2. I'm going to do it by just sort of iteratively substituting this into itself over and over again. So I'm going to start with m sub n, and I'm going to write it as 2 times m sub n minus 1 plus 1. And then what I'm going to do is I'm going to replace the m sub n minus 1. I'm going to come back to this formula, in other words, and I'm going to imagine that everywhere I see an n, I'm now going to use n minus 1. So the m sub n minus 1 would be 2 times m sub n minus 2 plus 1, and then we have a plus 1. Now, before we do that again, because we are going to just do that again, before we do it again, though, I'm going to recommend that we clean this up as we go along. So like I see a 2 times a 2. If I keep going like this, I'm just going to have a bunch of 2's out in front. Let's write that as 2 squared times m sub n minus 2. And then I also see a plus 2 and a plus, this is a 2 and a 1, right? I'm actually going to write it as 2 plus 1. I'm not going to simplify it to 3 because, again, we might lose the pattern because we're ultimately going to be looking for a pattern here. We might lose the pattern if we simplify this number too much. So let's just leave it as plus 2 plus 1. Okay, then I'm going to do the same thing again. I'm going to take 2 squared and I'm going to multiply it by m sub n minus 2, which I'm going to replace with, I have to replace that with 2 times m sub n minus 3 plus 1, and then plus 2 plus 1. Okay, and I'm going to once again clean this up. This is going to be 2 cubed times m sub n minus 3, and then plus 2 squared plus 2 plus 1. And you really want to be looking at the cleaned up version as we go along here. And the idea is you can keep doing this, of course, as many times as you would like. And if you don't see a pattern yet, of course, I encourage you to maybe take it a little bit further. Does anybody think that they could imagine like how this will ultimately shake out and reduce us down to what m sub 1 is? Because eventually we got to get down to m sub 1. You think we could do that? So let's try. If I want to have this be m sub 1, then instead of subtracting 3 from n, or 2 from n, or 1 from n, how much do I have to subtract from n if I want this subscript to be a 1? N minus 1, exactly. So I can think of this as m sub n minus the quantity n minus 1, and I'm emphasizing that subtracted part because it's the same as the exponent. It's the same as the exponent, which is in this case n minus 1, like so. And then what I'm noticing on the right here, and again, if I hadn't noticed it yet, I could take it another step or two. I'm noticing just various powers of 2, starting with the largest one being just one less than this one. So this would be 2 to the n minus 2, right? That's 1 less than this exponent, right? And then plus 2 to the n minus 3, and so on, dot, 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 plus 2 plus 1. Okay, and so because this is just m sub 1 and m sub 1 is equal to 1, I can just stop writing it. So this is really 2 to the n minus 1 plus 2 to the n minus 2 plus 2 to the n minus 3, and so on and so on, up to plus 2 and then plus 1. So we're just adding all of these powers of 2. Does anybody know what that adds up to? Does anybody know what kind of a series that is? Dare I use the word series in class? Oh, yikes, this brings back nightmares of calculus. This is what's called a geometric series. You can think of this, let me put a little asterisk here, and then maybe in your notes we can do a little asterisk. If you have, x to the n minus 1 plus x to the n minus 2 and plus dot, dot, dot down to plus x and down to plus 1, we actually have a nice formula for that, which is x to the n all minus 1 divided by x minus 1. If you don't believe me, just cross multiply it and FOIL it out, and you will see everything simplifies perfectly, right? So this is a finite geometric series, and obviously it doesn't work if x equals 1. Luckily here, x does not equal 1. This is, in this case, we're going to be substituting x equals 2. So if I do that, I would just get 2 to the n minus 1 all over 2 minus 1. And 2 minus 1, of course, is just 1. So this is 2 to the n minus 1. And that is the answer. That is how many moves it takes to solve Towers of Hanoi. So the 5 objects that I had up here on my desk, it would have taken me 31 moves to actually fully go through the solution to that problem. Okay? So we are solving a combinatorics problem by setting up a recurrence relation for that physical, and then solving the relation that we came up with. That is a pretty important technique, and we're going to practice it some more, a lot more. Okay. Questions so far, though? You can't get too far into this conversation about recurrence relations without talking about the most famous one of them all. And so I have to do that for the most famous sequence of all that comes out of a recurrence relation. Does anybody know what I'm talking about? The Fibonacci sequence. Yes. Famous. This is an absolutely famous example. This is a famous example because it's defined just as a recurrence relation, but then it has so many applications and sort of physical meaning behind it. So this is pretty well known. So Fibonacci sequence. The Fibonacci sequence. So let me just remind you, this one is sort of defined as a recurrence relation. So for this one, well, first of all, let's just write it down. I think you guys know that you start with 0 and 1. Those are the first two terms, and then to find subsequent terms, you just add the two previous numbers. So 0 and 1 gives me 1, and then 1 and 1 adds up to 2, 1 and 2 adds up to 3, 2 and 3 adds up to 5, and so on, and you just do all of these numbers, which are very special in the world of mathematics, 144 and so on. Pretty famous sequence of numbers, okay? But these numbers are famous and interesting because of the recurrence relation itself. It's not like the Towers of Hanoi, where you have the physical problem first, and then you develop a recurrence relation to solve it. Here, we're actually going to start with the recurrence relation. So for this, we're going to I'm going to use F's for these, which is the same notation as the book. F0 is equal to 0, and F1 is equal to 1. And then for n greater than or equal to 2, the nth Fibonacci number is the sum of the two previous Fibonacci numbers. This is it. So if I tell you the first two Fibonacci numbers, we can write down the rest of them just using that sequence. By the way, you might notice that on the Towers of Hanoi problem, I only wrote down one initial value, which was M1. I didn't write down more than that. Here, I've given you two initial values instead of one. And there's an obvious reason for the difference, which is that, right, this formula, if I want to be able to solve for Fn, I have to know the two previous values of the sequence. Whereas with Towers of Hanoi, I only needed to know one previous term of the sequence. This is related to something called the order of the recurrence relation. And when we get into the nuts and bolts of how to solve these things, I will put that into the notes as a definition. But for right now, it should just at least make, on an intuitive level, I hope it makes sense that you'd need two initial conditions if you hoped to use this to generate the whole sequence. I'm just curious, does anybody know the explicit formula? Or if there is an explicit formula for f sub n? Has anybody seen this?
It's the nasty square root of 5 one.
It's a nasty thing with a square root of 5 in it, which is another remarkable thing. Here we are in a combinatorics class with whole numbers, integers only, right? And now all of a sudden there's this crazy formula that has a radical 5 in it. So I'm going to write it down. The formula for f sub n is, so I'll start by writing down the formula. This is really remarkable. 1 over the square root of 5 times the quantity 1 plus radical 5 all over 2 raised to the nth power minus 1 over radical 5 times the quantity 1 minus radical 5 all over 2 raised to the nth power. And so, right? So here's, F0, here's F1, here's F2, here's F3, and so on. So you're telling me that if I plug in n equals 5 into this, I take the fifth power of this thing and the fifth power of this thing, and I do this subtraction, then it's going to be equal to 5. All the radical 5s are going to cancel, and as messy as it looks like from the outset, it turns out to have an extremely simple formula, and that is the case. Yeah, so you have to just imagine that these radical 5s, they just cancel like crazy. Probably when n is equal to 0 or 1, you can just see it almost in your head, but for larger values of n, it's, you might be a little skeptical about that. Does not look obvious at all. I would like to actually prove this, why this is the explicit formula. We can do things like this. So I'm gonna see if I can do this. I'll start the proof here. I'm gonna need to go to the other board, but I can at least start it right here. Here is the way we get this explicit solution. So to get this explicit solution, we are going to do a very, very high-powered mathematical technique to come up with the solution to this, which is that we are going to guess the answer. I always like when I'm doing differential equations too, it's the same thing, you know, you have some form of a differential equation which motivates a certain guess. And you're like, I had to go get a PhD to learn how to guess what the answer is. Well, specialists in these fields, yeah, that's what they learned how to do. But the trick is to coming up with a good guess, like to come up at least with something that's going to be close to the right answer. So that is what we're going to do. We will guess a solution of the form. And I'm going to stick with the book's notation on this so that you can read the book and follow along with the notes. I'm going to just guess for the moment that the form for the nth Fibonacci number is some power of q. So I'm going to say q to the n, where q is a constant to be determined. Now, we sort of already know that this is not going to work. Because you look at the formula for f sub n, it is not just the nth power of one single constant number. But at least this gives us a place to start. And one thing about this guess that's really nice, q to the n is a simple function that I can plug in everywhere into my recurrence relation. The recurrence relation is something that I do have in my hands that I can work with. So I'm going to come over here and actually do that. And we're going to see pretty quickly where this square root of 5 comes from. It's actually not such a bizarre thing, but let's write it out. I'm just going to plug the guess into the recurrence relation. So plug this guess into the recurrence relation, right? That's what I'm going to try to make this work. So f sub n was q to the n, and this would be equal to q to the n minus 1 plus q to the n minus 2. So those would be the terms here. And we can safely assume q is not 0. Obviously, if q was 0, we would have 0 for the Fibonacci numbers, which it's not. So I'm going to cancel as many q's as I can. And if I do that, I'll just get q squared equals q plus 1. I'll rewrite that as a quadratic equation, good old standard form here, right? Q squared minus q minus 1 equals 0. And now I can hopefully, it says over there, q is a constant to be determined. TBD means to be determined. And I can now use the quadratic formula to solve for q, right? Okay, so this is going to be what? 1 plus or minus the square root of 1 squared minus 4ac all over 2a. Does anybody know the quadratic formula?
Yes.
I hope so.
Not even better.
Please don't scare me. We'll have to bring some of the high school teachers in our crowd up here and give us a lesson on that. But yeah, so there you have it. 1 plus or minus the square root of 5 all over 2. So this is 1 plus or minus the square root of 5 all over 2. We actually have two values of q, and you notice that both of those are the values of that are being raised to the nth power here. Okay. And what we will do then is refine our guess for f sub n to include both of these, because we don't really know which one is right or if either of them is right. Okay, so what we're going to do is we're going to have a refined guess. First guess didn't quite work. As we said, we already knew it wasn't quite going to work, but the refined guess for f sub n would be that f sub n is equal to 1 plus radical 5 over 2 to the n, or 1 minus radical 5 all over 2 to the n, neither of which, and neither one actually works. When I say neither one works, I just know that these are not the correct formulas for the Fibonacci numbers. Because if I start plugging in values of n here with just the first part, I'll have a radical 5 in that expansion, which isn't going to be correct for any of these integer values. If I just use this one, it's also not going to work. So what we're going to do is we're going to take a combination of those two, a so-called linear combination of the two terms here. Yeah.
What was wrong with 1 plus the square root of 5 over 2? Like, how did you know to keep guessing?
So these would be, so if I use either one of these roots as the q value, and I said that's gonna be the answer and the formula is q to the n, then I can just look at this and say, well, if I plug in, I'll just plug in n equals 1. Well, if this was the right formula, what would f1 be? Well, it would be 1 plus radical 5 over 2. Well, that's not what f1 is. So we know this isn't matching the sequence. Yeah, so it's a good question. So we look at these guesses and neither one of them really works, but we could hope maybe somehow to combine them. Okay, so we form the linear combination. Can I say that in this class? I say it all day in my other classes. Teaching linear algebra, I can't get away from linear combinations to save my life. So we gotta have a linear combination, which is f sub n equals, I'm gonna say C1 times 1 plus radical 5 all over 2 to the n, plus C2 times the quantity 1 minus radical 5 all over 2 raised to the n. So we just can do that. And this time, this is with C1 and C2 to be determined. So now we're going to see if we can make this work. Okay. Well, if I want to solve for my constants, I can use certain values of n to do that. So like if I plug in n equals 0 into everything that's up here, I already know that f of 0 should be 0. So when I put in 0 for n, I should get 0. But when I actually plug it into the general formula that I'm guessing over here, I would just get C1 plus C2. Because those, when you raise something to the 0, it's just equal to 1. So that's not so bad. And then I might need to use another value of n as well, because I have two unknowns. So it's nice if I have two equations for two unknowns. My second equation, it would be f of 1. Okay, so I plug in 1 for n this time. And well, if I do that, I have to work a little bit harder. I have C1 times the quantity 1 plus radical 5 over 2 plus C2 times the quantity 1 minus radical 5 all over 2. And so from the first equation, you can see that C1 and C2 are just negatives of each other. So what you could do is you could just turn this into a minus C1. And so what that would give you is 1 plus radical 5 over 2, and then just turn this into a minus and factor out the C1 from this. So you have something like that going on. And that becomes actually just radical 5 times C1. I'm doing the math kind of quickly in my head here. But that's just gonna, that part in the brackets just becomes radical 5. It just becomes radical 5. The denominator of the fraction of 2 goes away when you combine those like terms. And so we just have radical 5 times C1 equal to 1. So C1 becomes 1 over radical 5, and C2 becomes negative of that. So negative 1 over radical 5, and that is exactly how you get your formula. It's exactly how you get the formula. Okay. Clear enough so far, anyway? This one doesn't have, you know, the puzzle behind it to motivate setting up the recurrence relation. This is just a recurrence relation that somebody set up and said, something interesting, we'd like to solve it. And it is a very famous sequence. That's my, oh, I'm doing good on time. Okay. I will tell you that, sorry, Nikolai?
I'm just curious about. Proof of something like that, like.
You want more rigorous? I can let you do it, have someone help you. You mean if we had like more terms here that it was a higher order?
Yeah, like the starting point.
Yeah, because this equation in this case was only a quadratic. Is that what you're talking about?
Yeah.
It would just be, the concept of it would be the same though, wouldn't it? It would just be a messier version of the same kind of problem. You'd have more constants to solve through. You would do exactly this format again. You'd have C1 times your first root to the n plus C2 times the second root to the n and so on. You would just do that same procedure. It would just be, from a practical point of view, a messier calculation, but the concept of it should be about the same. Okay, you okay?
Yeah.
Awesome. Because these sequences are often defined through the use of a recurrence relation, which describes the terms of the sequence in terms of earlier terms of the sequence. A lot of things that you prove about these types of sequences is done by induction. And that I hope is something that people are a little bit familiar with. I will say that sometimes if you haven't done it lately, it can be a little rusty. And it might be worth practicing that. So let me just make a quick remark here. Does everybody agree I'm done? I'm pretty much done with this proof because I've solved for C1 and C2. If I put those in here and here, I get the formula in the box. So that's kind of where I'm drawing the line on this calculation. Yeah. Okay, so my remark then is that proofs involving recurrence relations often depend on induction. So we are going to see some proofs by induction in this chapter that you're going to have to look at. By the way, the homework assignment that's the next one up is going to be due next Thursday. So you'll be able to at least get a decent start on it, I think, before Thursday, or before next Tuesday. But I will obviously be covering some stuff on Tuesday as well that will help with it. But you can start, based on what we've already done, and at least get a start on it. Let me give you an example of the sort of thing that you could do. We could ask you to do the following. For all positive integers n, so I'll denote that as n in z plus, prove the following formula. So I could ask you to prove that f1 squared plus f2 squared, so this is with the Fibonacci numbers, up through fn squared. So if I add up the squares of all of the Fibonacci numbers, I end up getting the product of the last one with the next one after that. So fn times fn plus 1. So we could ask ourselves to prove something like this. And I'm going to do that just to get induction back in your mind again for a minute. Does anybody remember what the pieces are that are required on an induction proof, Teresa?
You need to show that the base case is true, and then you assume that it's true for your f of n,
Uh-huh.
and then you need to prove your f of n plus one is true.
Okay, so there's sort of two parts to it. You have to do a base case, which is sort of like the first value of n that you have. So if I'm indexing n with positive integers, the base case would be n equals 1. And then you have to prove that if the sort of the n version of the formula is true, then the n plus 1 version of that formula is true as well. So for this proof, so Teresa's got it exactly right. I am going to start with the base case. Now, I should also mention that sometimes. Okay, so let's just see how you guys are with this. Do you remember that there is a strong version of induction as opposed to just like regular induction? Yeah, so normally, you know, the regular induction is exactly what Teresa was just describing, where, you know, you use the sort of the n version of the thing you're proving to prove the very next version, right? As long as that's the version that you're using, you only need to check the first base case only, the very first value of n. So in this case, that would be n equals 1, right? But if you notice that your proof is using the strong version of induction, and I have to admit, the strong version of induction is really no stronger than regular induction. But if you use more than just sort of one case to get to the next case, then you have to have as many base cases established in the beginning as you're going to need in terms of like previous cases to build the next case. If that makes sense.
So like for the Fibonacci sequence.
It depends on what the relation is. It depends on what the relation is. So even though the Fibonacci relation, so our Fibonacci relation is this. So I agree that, okay, we need the two previous Fibonacci numbers to describe what the next one is. Whether we need two previous versions of this formula to prove the next version isn't clear to me yet, right? It depends on the problem. So I'm going to recommend you, as a base case, you always have to do at least one base case. I'm going to start with n equals 1. And we can allow ourselves, of course, to come back to this later. So if we get into the induction step and we recognize that we're going to need several versions of this formula to prove the next one, if we're going to really do the full-blown strong induction, then we can come back and add more base cases. Usually the base case part is easy, right? But you really do have to be careful. So if n is 1, this left-hand side is just f1 squared, and this right side is just f1 times f2. And is that correct? Let's see. So remember, f0 was 0, f1 was 1, and f2 was also 1, I think. That was how the sequence started. So you can just check that, yep, that works. That's just 1 squared equals 1 times 1. So for my base case here, it certainly works. Okay. Clear enough? Then I'm going to do the induction step. So for the induction step, we're sort of going to assume the formula the way you see it, right? So I will assume, we have to assume the formula, so that's f1 squared plus f2 squared plus dot 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 plus fn squared equals fn times fn plus 1. And then I'm going to prove the next case. So then, and in this case, I think we'll be able to do it pretty quickly. f1 squared plus f2 squared plus dot 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 plus fn squared plus the very next term would be fn plus 1 squared. Now guys, if you need a little checking on this write-ups of these proofs by induction, be sure to stop by my office hours as you start practicing these. I don't want to see chicken scratch on both sides of the equal sign, right? This should literally be white space down here, right? We don't write on this side. I don't know how your 280 teachers do this, but I like to start here and then just a series of statements here. And hopefully on the right side, we'll eventually get the n plus 1 version of this. which should be what, Fn plus one times Fn plus two. Okay, so let's see what that happens. How would you suggest that I think about this piece? I'm sorry?
Block it, because we see that F1 squared plus F right there, and then right after Fn.
Yeah, I actually can see all but the last term is already written down as my assumption statement. So I can go ahead and do that and just replace it. So Fn times Fn plus one, and then we have plus Fn plus one squared. Nice. What would you suggest we do with that? Which is, I can factor the Fn plus one out, and then it's left with Fn plus Fn plus one, like that. It's just basic algebra with that. And then I have Fn plus one, and this is just going back to the recurrence relation. This is Fn plus two. And so we can put a check there, and we have completed the induction step. The important thing here, so getting back to the comment Amber made, which is a really good one, that we only used the n version to prove the n plus one version. So I only need one base case to get this domino of statements to be proved, right? If we had been working on this and gotten sort of fumbled up somewhere, or maybe we saw the not just the n version, but the n minus one version of this formula, like the previous one, and we were using that in our proof here, then we would have to acknowledge that, oh, well, I have to know two previous cases to prove the next one. So I better have two base cases just to get the ball rolling first. So this is how these are done. Do you guys like this proof? Actually, I'm asking for a reason, because I don't do induction this way. Right. So instead of assuming the n version and proving the n plus one version, it's absolutely just as correct and just as okay to assume the n minus one version and prove the n version. I see some of you nodding. Did you learn it that way? Oh, you did? Oh, this is my problem. Okay, so the last time I taught the class, I think I did the n minus one to n version, and everybody was like, wait a minute, I want to, whoever taught the induction, and for those folks had assumed the n version and proved the n plus one version. If you like the other version better, especially if you've learned it that way, is totally okay, right? It's equivalent. I like assuming the n minus one version and then proving the n version, because then the thing that's asked of me right here is literally what I'm going to try to prove. Rather than assuming, one of the worst mistakes of proof techniques that we ever see is when people assume what they're trying to prove, right? So instead of assuming this and then proving the next version, you can, if you don't like that, then you're kind of in my camp. You can come down and we can throw a party in my office, and I'll agree with you and say, yeah, I'm with you on that. What professor would ever teach it the other way? There's a lot of people do. Yeah, and I love all these people, by the way. But yeah, people do it different ways. Okay, so anyway, I just wanted to give you a heads up. There's a little bit of induction for you guys to practice on the homework for next week. Let's go back though to the two-step program. And I'd like to do one more example today before we run out of time here. This is the setting up the recurrence relations business. On Tuesday, I'll focus more on the cookbook process of how do you actually solve these things. I just want to get this set up. So setting up recurrence relations is a big deal to being able to do this section. So setting up recurrence relations. And well, like everything else in math, it takes some practice to kind of get good at this. So I will give you an example, I think. And we'll see if we can do it. Okay, so we're just going to practice an example. So this is the example. I would like to find a recurrence relation. Notice I say a recurrence relation. As we mentioned earlier, they are not unique. And so we have 30 people in here. We could have 30 different recurrence relations that are all correct. That is possible. for the number, let's call it Z sub n, of bit strings. Does everybody understand? That's just zeros and ones. Bit strings, just a string of zeros and ones. Of length n. So this is length n that contain. If I just said, give me the form, if I stopped and I didn't have any more conditions, you would just tell me that Z sub n is 2 to the n. I have zeros and one, two choices for each side. You wouldn't need recurrence relations. You just write down the formula and go home, right? So here, I'm gonna make this a little harder now. These are bit strings of zeros and ones that contain 2 consecutive zeros. Aha. That's the extra little trick here. So these are bit strings that have 2 zeros in a row somewhere. And that means you could have 3 in a row or 4 in a row, as long as somewhere as you scan this string, you see 2 zeros right next to each other. Right? So I don't want to actually get the explicit formula for Z sub n right now. I just want to try to write down the recurrence relation. And the way we do this pretty quickly, and then we'll be good to go. We're going to break up these bit strings into cases. Okay, so I'm going to create non-overlapping cases. And the idea here is that I'm going to take my string of length n and try to express it in terms of a string that is shorter, right? Recurrence relations are supposed to describe Zn in terms of, say, Zn minus 1. So for example, I could have a string that starts with a 1, and then the rest of these n minus 1 slots would have to be where the 2 zeros in a row would occur, right? Because they're obviously not going to involve this first slot, right? So in this case, I would say just in this case alone, let's put a little note over here on the side. There are Z sub n minus 1 strings here with 0, 0. I'm just going to write 2 consecutive zeros with 0, 0, 0. So I don't know how many that is, but in terms of the notation of the number of strings of a certain length, this is now a string of length n minus 1. And if I've got 2 consecutive zeros, it's definitely got to happen there. Okay. Now, you might think that my second case would be to just start with a 0. But the problem is that then it's possible that the next slot is also a 0, or maybe it isn't also a 0. And if it is a 0, we want to count all of those. But if it's not a 0, well, so if it's like this, then we're back to, n minus 2 slots. And that's actually going to be my second case. I'm going to use a string that looks like this. And I'm just going to say, well, in this case, there are Z sub n minus 2 strings with 0, 0 in them. The 2 zeros in a row would have to occur in this part of the string, right? I can't have 2 zeros in a row that involves the first 2 spots, right? By the way, what I hope that you will be agreeing with here is that these cases are not overlapping. You cannot have a bit string that is listed here and here. And that by the time I'm done with all of these cases, every type of string fits into one of the cases. So the only thing I'm missing here would be strings that start 0, 0. And of course, then I have still n minus 2 slots. Right? You might wonder, well, why didn't I do, to follow the pattern, why didn't I do 0, 0, 1? Because I seem to be doing that. I started with 1, here I do 0, 1, here I do 0, 0, 1. The thing is, as soon as I have 2 zeros here, then actually I don't need to break this into more cases where, depending on what the third position is, because all of these strings have 2 consecutive zeros in them. So there, we can actually write it down. There are, let's not make more cases than we need to make. There are a full 2 to the n minus 2 strings in this case that have the 0, 0 in them. All of those strings, and that's how many strings there are that have that form. And so then by the addition principle, adding, right, we get our relation. Zn equals Zn minus 1 plus Zn minus 2 plus 2 raised to the power of n minus 2. That would be the answer. Yeah, Julie?
I think we just do, starting with a 0. And then not, because couldn't the n minus 1 slot start with a 1 or start with a 0?
Yeah, well, that's basically what I ended up having to do is sort of make 2 cases out of that. So if they start with a 0, I could just collapse this into 1 case, but then I would have had to ask myself, well, some of them would go from 0 to 1 and some of them would go from 0 to 0, and I'd be counting them mentally. I would still have 2 things to add together there. So I'm just trying to be explicit and kind of listing those cases. Does that make some sense? Yeah. We'll come back next time, guys, and practice a little more of these kind of things. But before I let you go, I just want to give you back your exam. Quick note on the exams. I said the exams were really good. The only one that most people did not get was the one about the probability of the arrangements.
That was a 0.
And I know that I only talked about this briefly. So it was only a little 4-point question. But the thing with that probability thing is that it oscillates up, down, because the formula is like switching from positive to negative. So every time the n switches from even to odd, you're like adding or subtracting or adding and subtracting. So it was, a lot of people just put them in order,
Yeah.
either this way or that way, but it's a little trickier than that. Don't worry about that one. I obviously didn't prep you well enough to get that one. But other than that, the average was about 70%, almost just a hair under 70. Yeah, there were 3 people above 90, 5 people in the 80s, pretty good scores. I was overall pretty happy. But if you're not happy with this, don't feel too good about it. I hope that you'll feel free to stop by. You can talk to me about it. I'll give you advice on maybe what you could have done differently or suggestions for next time. Whatever the case may be. But I'll pass these back and then I'm gonna let you go. So Kaden and Melissa.
Yeah. Yeah.
And
I know, we were on the same station. Yeah.
What are you?
Yeah.
Down, and you are. That's you. Thank you. Yeah, senior. Sorry, I get you guys confused a little bit. E.
You look tired.
First time I'll see you. So Maddie. Maria. Mitchell.
This was better. Student circle. I couldn't put the light, I was like, what? Like, what? You guys. Yeah.
Khalil. See who's over there. Awesome. Dow. And Nikolai. Oh, Amber. Welcome. Everybody. Guys, have a great great rest of your week and weekend, and we'll talk again soon. You have an answer?
Why doesn't this change?
Go ahead.
Why that's going to be all. So this includes 1 and 0.
They have zero.
On the specific period. It's like, I don't even tell you when the first is. And then, but this could. Now, if you. Let's say. And which is not wrong, and you get out of the case, it looks like this, except when you have to throw that. Why would you, right? By the choices, that's right, that's right. I know.
Yeah, that's why I wanted to ask you, because you mentioned so I was wondering if.
I was worried about it until I looked at it.
No, that's the thing,
I knew that to solve it.
I barely just run for the stuff. That's why I wanted to ask you. Would you have allowed me to use the same form? You said it was a good question.
I-
That's the thing, I just finished them.
I was gonna say you solved all the problems, and so if, but that's partially, you have to make sure you read those correct.
That's the thing,
Yeah, so, yeah, but anyway.
Better with almost thing, I just didn't really think like, remember you. But. This is.
You're still doing, you did pretty good. I know it could be a little better, but yeah, I know. Next time, you got it.
Just for the future.
You should just be sure you're checking the rules, which are on the front of the text. And if there's any question, they're supposed to be able to reach over to me.
That's the thing, we tried to do that, like,
Okay?
because I can finish it.
Oh,
We tried to contact you.
well, I was probably here right at 5:30, but I just didn't get anything from your, did they try to call me?
I think they did. But then
I had a call on my phone from a 6'5". I didn't know who it was. I don't usually answer the phone if I don't know who it's from. So all the DSS people that unless Dr. Annan knows that it's coming from DSS, he's not going to answer it.
next time I'll have this out.
Thanks.
They can,